We'll move on directly to the next speaker. Lynn Hildemann and I go way back to days as graduate students at Caltech. We had the same PhD advisor. When we met this morning here, Lynn remarked, it's pretty remarkable that I have to fly across the country to see you because we work 40 miles apart in Stanford and UC Berkeley. Anyway, we're really happy to have you here, Lynn, and look forward to your presentation. Thank you.
Thanks. So my task within indoor sources is to talk about indoor combustion sources and indoor allergens. So like the previous talk, kind of two mini talks in one. And let's see, try that. There we go. No? There we go. So let me start by talking about combustion particulate matter. The vast majority of combustion particulate matter is submicron in size, and it includes substantial amounts of ultrafine particles. The chemical composition of combustion particulate matter has received a lot of study, kind of taking a big picture look at it. It's a lot of different organic species, along with varying amounts of soot, depending on the type of combustion process. And some combustion sources that you commonly find indoors have in fact been well studied. Lots and lots of study regarding the composition, the size, and both the chemical and size evolution with time of cigarette smoke emissions. Not quite as much work done on incense, but certainly again some measurements regarding the composition and particle size characteristics of incense smoke. And another category that's received a lot of attention is wood combustion, where the focus there, besides the chemical composition, has been under what circumstances do wood combustion emissions end up in the indoor environment as opposed to going up the stack. And observations are that stirring up the fire, or when you first start the fire, or if the flue draws poorly, are all examples of when you can get some of these wood combustion emissions inside your home. Now, since we all have limited amounts of time here, I wanted to devote most of my time to what areas need more study. Where are there gaps or shortcomings in the information? The first one I want to draw some attention to is cooking. The indoor emission rate depends so greatly on both what type of food you're cooking or types of food and your cooking style, whether you're grilling or frying or baking. Now, many people, when you think of cooking, you probably don't think of air pollutants. You think of wonderful smells wafting through your home. So it may be a little upsetting to think that cooking is actually a source of indoor pollution, but it is. And a very interesting factor is that the emissions not only depend on what kind of food you're cooking and how you're cooking it, but they also depend on what kind of ventilation strategies are used. I would say almost all of us have a vent up above our stove. It turns out that only a small fraction of people actually turn on the vent in a consistent manner. In addition, there are styles of vents that, while they draw the emissions away from the cooking area, they then vent them out up higher up near the ceiling as opposed to sending them outdoors. So that's not so helpful for removing the smoke from the indoor location. And so while there have been studies measuring certain specific kinds of cooking and what emission rates are associated with them, and also some chemical characterization of those emissions, there's a lot left to be done. In particular, I'm sure it's never happened to you that you've burned anything in the microwave or in the toaster, but that turns out to be a way to really very quickly introduce a lot of particulate matter into the indoor environment. So anyway, a lot of work remains to be done on not only the nature of heating the pan, which the previous speaker talked about, but also what you have in the pan. Even the type of oil you use if you're frying can make a big difference for what you see in the emissions. I think I'm going to talk about e-cigarettes second. E-cigarettes are certainly receiving a lot of attention now in terms of where you can smoke and what is being emitted. When I look at the literature so far regarding emissions from e-cigarettes, it's certainly clear that ultrafine particles can form, and several studies have suggested it's mainly from condensation of a condensable organic species that's used to help deliver the nicotine. Where the studies are all over the place is in terms of the sizes of these ultrafine particles and also in the re-evaporation rate. The same processes that are going to cause these ultrafine particles to form as the emissions further dilute and cool in the atmosphere, the dilution can cause re-evaporation. And the difficulty or shortcoming of the current studies is they're made under controlled laboratory conditions. And so it's possible to either under or overestimate the lifetime of these ultrafine particles depending on how you set up the experiments. But I don't think there is information out there that I yet trust in terms of reflecting what you might see if you were indoors with someone who was smoking an e-cigarette. Natural gas emissions or combustion emissions from things like stoves and ovens are a very important source of ultrafine particles in the indoor environment. Natural gas is a very clean burning fuel, and because of that, when species in the emissions condense, there's very few particles for them to condense onto, and so they tend to form their own ultrafine particle concentrations. Again, this is another area where persistence in the indoor environment is not clear. Do these ultrafine particles last for a few minutes or a few hours? In the case of natural gas, what are they composed of? Are all questions that have not been completely answered yet or well studied. All right, well, there's a few other sources that you might not think of smoke that I wanted to draw your attention to, and one is your neighbors. If you live in apartments or condominiums and you have neighbors next door or underneath you who, for example, are cigarette smokers, then intrusion or infiltration of secondhand smoke into your unit from these neighboring units can be quite substantial. It can infiltrate from outdoor areas, like your balcony, if you open the windows, and it can also be carried through the walls and through ducts from one residence to the next. And this is a problem that's only going to be growing as more and more people buy condominiums or live in apartments as opposed to having your own separate, isolated dwelling. And there's a lot of considerations related to how is the building constructed, how is the ventilation system designed, in determining to what extent this can be a problem. I want to show you one example of secondhand smoke intrusion from an area where a smoker was smoking into not one but two units that were above where this smoker was smoking. What you see here in these measurements is that before those shaded boxes was what the background concentration of particles were in these two non-smoking units. We're down at just a few micrograms per meter cubed of PM2.5. And then what these measurements saw almost simultaneously, was a great increase in the indoor particle concentrations in these two units due to this person smoking underneath. And the interest in this study was, can we prove it's smoke from cigarettes as opposed to someone burning stuff in the microwave, for example. And so chemical characterization was done on the particulate matter collected and using chemical mass balance approaches. We showed that 98 to 100% of what that elevated PM 2.5 was due to secondhand smoke. And so it's very telling to have indoor particle concentrations jump up to 40 to 70 micrograms per meter cubed due to nothing that's going on in your own living space, but due to what your neighbors are doing. And I feel this is an area that needs a lot more study because there are so many factors related to building design and human behavior and other factors as well that contribute to this. Another area I feel that needs more study related to your exposure to combustion emissions indoors is how close you are to the source. And so you can see in this photograph the smoke from a burning cigarette, and it doesn't immediately disperse throughout the room. So if you happen to be in close proximity to an active combustion source, then you're going to be breathing pollutant concentrations that are much higher than what you would predict for a well-mixed average in the room. This is especially important in residential type buildings using natural ventilation, where the rate of mixing indoors can be significantly less than what you would see under mechanical ventilation conditions. And so the question is, well, how bad is it? How bad is it to be close to an active combustion source? And this plot gives you one idea. This was a tracer study. And what the x-axis is showing is how far away you are from an active emission source. This particular tracer study was using carbon monoxide. And then what's plotted on the y-axis is a normalized concentration, where the measurement is divided by what you would have predicted if the room were well mixed. So if the room really was close to well mixed, you'd expect all these measurements to be down very close to 1. But in fact, what you see is if you're within 1 meter of the source emissions, you can experience concentration levels that are 10 to 20 times as high as the well-mixed average. And the level of elevation of the exposure varies with air exchange rate. And what's kind of odd when you first look at it, but it makes sense, is that when ventilation rate is highest, the proximity effect is the worst. And the way to think about it is as you increase your ventilation rate, you are decreasing the well-mixed average concentration, but you're not having nearly as much of an effect on that cloud of emissions close to the active source. All right, so this concept of proximity and of worrying about exposure levels not only as a function of whether you're indoors or not, but where you are relative to active emission sources. This is going to be especially important if you've got sources that only emit for minutes or a half hour at a time, where that concentrated cloud is going to be especially high compared with the well-mixed average concentrations. But this is also important to consider in terms of particle size. For example, if you think of very large particulate matter that has very significant removal rates from the atmosphere via settling, then it's a big deal whether you're close to that source of large particles or not, because if you're farther away, the particles will quickly settle out and you will not be exposed to much of them. It's equally important for ultrafine particles for the reason that ultrafine particles do get removed fairly rapidly via coagulation. And so you would not expect UFPs to reach a well-mixed uniform concentration in a room. Instead, they're going to vary with their distance from the source. Now, looping back for a moment to talking about food, whoever is doing the cooking and standing near the stovetop is going to experience higher exposures to the emissions coming from the cooking. And so there's also considerations as a function of how individuals spend their time and, for example, who does the cooking in a household. All right, let's move on to the second mini talk on indoor airborne allergens. The indoor environment's a very exciting place for allergens. Not only do you get dander, that is skin flake shedding from cats and dogs, that people can be allergic to all by themselves due, for example, to the saliva from the cat. But these skin flakes also contain bacteria, and we human beings also shed skin flakes. A lot of people talk about being allergic to house dust. And in fact, what they're allergic to are some of the allergenic components in house dust. You'll find things like mold and bacteria in house dust. You'll find mite antigens, cockroach antigens as well. And the house dust can be easily resuspended. And the next speaker will be talking more about how resuspension occurs by things like human activities. And then kind of the last general category of indoor source I would call damp surfaces. You can find damp surfaces in bathrooms, places in your house where condensation occurs, where you might have leaky pipes, for example. And this encourages molds and some bacteria to grow. A lot of times in thinking about molds, about fungus, you think about outdoor sources coming indoors. But in fact, there's certain kinds or genuses of aspergillus, like aspergillus and penicillium, that really like the indoor environment and really thrive there. And so in fact, for some species, you find higher concentrations indoors than outdoors. Now, I had said for smoke that those particles tended to be submicron. When you look at airborne allergens, the sizes vary much more widely, varying a little with type of allergen, but the main thing I want to point out is even within a category, there's a broad range of particle sizes. And this means that there's quite a range of residence times in the atmosphere, and it will vary in terms of where it deposits in the human lungs. As just one example for mites, the reason there's such a broad range of particle sizes is because the allergens are both present in mite feces, which are larger size particles, but they can also be present on little bits of exoskeleton that the mite molts off. So big deal because of where things deposit in the respiratory tract and the clearance times out of the respiratory tract. Now, for house dust, since it's such a rich source of particles, even though I'll leave kind of human activities alone, I did want to say a little more about vacuuming as a source of allergens. This plot shows what is fairly typical that you would see a person exposed to while using a vacuum. So a 2 to 5-fold increase in concentrations of fine particles of different sizes. Some have hypothesized, oh, this is the vacuum wheels kind of stirring up the dust, or it's less than 100% efficiency in capturing the dust out of the carpet. What I want to show you is this is one vacuum. Another vacuum, the exact same model, also fresh out of the box, brand new. Same experiment. Suddenly, no change. Very little change. And so what was going on here is just minute differences in how well the filter on the exhaust fit into the filter frame. So this goes back to Bill's earlier work on kind of as a function of the crack opening, how much stuff can, in this case, bypass the filter. So this particular vacuum out of the box happened to have its filter, its HEPA filter seating very tightly inside the filter frame, whereas this one, also with a HEPA level filter, must have had small cracks that allowed a lot of the particles to bypass the filter. All right, areas where more study is needed on airborne allergens. One important area is relating to these damp surfaces. We know that bacteria and fungi grow on these damp surfaces. They can grow on all different types of material. We don't know, or very little is known, about what determines the emission rate, the release into the air of these allergens. A little work's been done looking at airflow. It's been hypothesized that vibrations in the room might also play a role. But very little is understood here, so we don't really know how to accurately estimate emission rates from damp surfaces. The other area where more study is needed is looking at how individual activity patterns influence exposure to allergens. And so, for example, whoever in your house dusts or vacuums is going to be exposed to a lot more allergens. If some individuals in your house spend more time in the home than other people, they're going to be more liable to be exposed to these allergens. And in particular, I know there have been a lot of studies looking at gender differences in allergenic symptoms and in levels of allergen complaints. I don't know as much has been done trying to incorporate in the role of differences in human activities on these exposures to allergens. And as a final thought, because it's time for me to finish up, as we go through our experiences on global warming and how they might impact the indoor environment, what jumps out to me is that to reduce costs of air conditioning, people are going to put in more efforts into tightly sealing their homes, lowering the air exchange rate that Brent talked about. That's going to allow any indoor source emissions to build up to higher levels. As it gets hotter outside, people are going to spend even more of their time in the indoor environment. And finally, due to this combination of air conditioning and/or lower ventilation rates, we're going to tend to see higher humidity levels indoors, and therefore have conditions that are going to be even more favorable for growth of things like mold and bacteria and mites as well. That's it.
Thank you, Lynn. Our